Please start, sir. We are live.
Okay, so to the first problem session for Algebra 1. And you can type in all your questions into the chat. And while you do that, let me begin by questions that you have already asked in the in the form that we sent to you. So so the assignment 2. So I think the notion of wreath products, which was introduced in the assignment, needs to be explained a little more carefully so that you can all understand it better. So let me start by explaining this in the context of problem 8. So problem 9. So here's what we do. So we have this group which is denoted G wreath Z mod 2Z. Studied semi-direct products. So let me explain what this means. So what this means is we take the group G cross G, and this group has an action of by you think of these two coordinates as corresponding to the elements of Z mod 2Z. So this corresponds to 0 and this corresponds to 1. And what you do is, yeah?
Is your screen shared? We're not able to see.
Not sharing. One second. Yeah, sorry about that. So, yeah. Okay, so G has an action of Z mod 2Z. And how does this action work? So you have two elements here, 0 and 1. Acts on G1, G2 by interchanging the two elements. And of course, 0 being the identity has to act by identity. Work. So I think there was an issue with the problem 8 itself. It's not very clear what is meant by this wreath product there. And the proper framework for a wreath product is that you have a group G on which G acts. You can take, can always take X to be G. So this is a little more general than what's described in problem 8. So G, if X is G, then just G acts on itself by left translation. And now what you do is you define the wreath product with respect to this action as follows. So so H wreath G is H to the power of the cardinality of X semi-direct product G. So here you have, suppose X has n elements, this would be H to the power n semi-direct product G. So here you would index the elements of H to the x1 hxn, and your element G will act on it by H of, I guess I have to put H of Gxn, where this is the usual action of G on X. and then you just take this semi-direct product. So that's the notion of special kind of semi-direct product. So in this, in problem 9, what we're looking at is two copies of G, and then the element, non-trivial element of Z mod 2Z interchanges those two. So I hope better how to solve that problem. Let me see. Okay, what is the next question that? Okay. So in question number 8, there's a mistake. The answer should be, of course, answer should be just as the problem is stated. The group has order cardinality of G to the power H. So that's like 2 to the power 6 times 6. So the answer is not 48. The answer is 2 to the power 6 into 6. Okay. So yeah, there's also a mistake in problem 12. So let me just clarify that. Problem 12, the problem is fine. The solution given, answer given is wrong. How many elements? How many triples X, Y, Z such that X, Y, Z equals E? And as one of you correctly pointed out on the discussion forum, so in the Quaternion, you can choose X and Y arbitrarily, however you like. You can take Z to be X, Y inverse. So there are 8 choices here, 8 choices here. So 8 into 8, 64 choices. And for each choice of Z, so there's exactly 64 triples X, Y, and Z, such that X, Y, Z is the identity in the group Q. Krishna, you're asking if one acts trivially. So in principle, yes, one can act trivially, in which case that semi-direct product just becomes a product Z mod 2 cross Z mod 2 cross trivial action. So normally when you just write Z2 read Z mod 2, you assume that the action is non-trivial. So here this could in principle, yes, you could have one G1, one G2. If you do this, then G read Z mod 2Z is isomorphic to Z mod 2Z, but that's not usually the convention. That's a good question. You could take, so what I was saying is, in general, you could take any group acting on any set and construct a Reith product from that. Okay, so you take is the group you take here is a symmetric group Sn, and then you take n copies of H, and you just take Sn acting on the n copies by permuting them. So that's the most common. Okay, So Chandan has asked, what is an automorphism and what does it signify practically? So an automorphism is, and morphism means transformation. So an automorphism is a transformation in general for any mathematical object. An automorphism is a transformation of an object, of a self transformation, which preserves its structure. A self transformation which preserves structure. So, how would you? So, what we have talked about is graph automorphism. What is a graph? Well, a graph is a set together with a collection of edges. So, vertices and edges. So, this E is a collection of subsets of size 2 of V. And so, you can think of this as the structure. And this E puts some additional structure on the set. And a graph automorphism is then a function G from V to V such that if uh, if X and Y, if this belongs to E, if this is an edge, then X, GY is also an edge. And maybe I should put curly brackets here because you think of this as undirected graph, so these are subsets. So it's something that preserves structure. But we can also talk about what is a group. Well, a group is a set together with a binary operation, which I will denote by dot, and it has a distinguished element called I. Has a function which takes x to x inverse. So it has the inverse function. And one could define a group automorphism as a function G V to V, G of E. G preserves this, all this structure that is on it. So this is the structure. So G of x dot y is gx dot gy. This is what it means to preserve a binary operation dot. Preserving, sorry, g is from not v to v, but rather from g to g. All x, y in g. And then you would also have g of e is equal to e, g of x inverse. Okay, so in a sort of very formal sense, whenever you have a structure, so it could be a group, it could be a graph, but more generally you could have a geometric structure, it could be a metric space, or it could be a poly. Always talk about its automorphisms, which are functions from this structure to itself, which preserve from this set to the underlying set to itself, which preserve its structure. So interesting. Let me just do an example of a way to compute the automorphisms uh, of a slightly more complicated graph. So let's look at the following graph. So it's got 10 vertices. 5 on the outside and side. So this is the Peterson graph, and we could ask what is its automorphism group. So, so this looks like a difficult problem in the sense that do you really have to go through? So there are 10 vertices, so you have 10 factorial possible, and you need to check which of them are graph automorphisms. Possible job, but let me try to convince you that the automorphism group of the Peterson graph of order um, is of order uh, 6 120. The automorphism, let's call this gamma. I claim that aut gamma is isomorphic to the group S5. So this is of order 120, which is much smaller. So here's a very interesting way of getting the Peterson graph, which makes this why is this S5 is appearing very clear. So consider the set. Let's just use this to the first 5 positive integers. And now let's look at V to be the collection of all subsets of size 2 of 5. So how many subsets of size 2 are there? 5 into 4 divided by 2, which is 10. So that's the number of vertices in the Peterson. Uh, so this V is, I can write down all the 10 points. So 1, 2, 1, 3, 1. By this I mean the subset whose elements are 1 and 2. I'm not going to write 1 and 2, it becomes difficult to write. So I'll just use a shorthand. And then 2, 3, 2, 4, 2, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these are the, and let's try to define an edge relation on this. So say that ij is connected by an edge to KL, J and the set KL are disjoint. So so this gives an edge relation on this graph. So let's try drawing it. I hope I can do this nicely. So I have one, and this is connected to. So there are 3 sets that are disjoint from 1, 2, namely. Uh, so the remaining 3 elements are 3, 4, 5. So 3, 4, 3, 5, and 4, 5. And now each of, so 3, 4 is connected to 1, 2, but now I'm also looking at so the missing elements here are 1, 2, and 5. So 1, 2, of course, and then we have uh, 1, 5, and then we have 2, 5. And then we have from 4, 5, we have the element. So here 1, 2, and 3 are missing. So we can take 2, 3 here. And the other element is 1, 2, and 3. So 1, 3. And these two are connected, and we have two more elements here. So I think 1, 5 is so missing 2, 3, 4. So we have 3, 4, 2, 3. So 2, 4 here. And this is missing 1, 4, 5. So we have 1, 5 and 4, 5. So we must have 1, 4 here. And these are connected. And what we get is these are connected. So what you see is that this actually defines the Peterson graph. So the resulting graph is isomorphic to the Peterson graph. And so now if you have any permutation of S5, so if sigma belongs to S5, then sigma also acts on V. How? Sigma of ij is, maybe I'll write it like sigma dot ij is equal to sigma I sigma j. You just act on the points. And now if ij and kl are disjoint, then sigma I sigma j and sigma k sigma l are also disjoint. And so this gives rise to an action of S5 on V and preserves the edge relations. And you can, so what you get is a homomorphism from S5 to automorphisms of the Peterson graph, which I'm denoting here by gamma. And you can easily check that this is injective, that is, only the identity gives rise to the trivial automorphism. And you need to show that it is surjective. And this you can do using the uh, uh, orbit stabilizer lemma, that is, you find how many automorphisms fix one of the vertices of the Peterson graph. And then using that, you can compute the order of the automorphism group, like we did for the cube graph in the lectures. So that's a very interesting non-trivial computation of the automorphism group of a graph. Um, in a lot of examples, I mean, there's a lot of algorithms to compute the automorphism groups of graphs very fast, and they tend to realize this automorphism group as a subgroup of a symmetric group, what is known in computational group theory as a permutation group, a subgroup of the symmetric group. And you can use software such as Sage to compute the automorphism group of a graph. You just construct your graph and ask the software to compute the automorphism group. So, Krishna, I'm not sure if you can't define the edge relation in general, how do you even have a graph? I mean, So unless you know what the graph is, how can you ask? So if you don't, but if you don't have a nice understanding of your graph, then you're left with only brute force to try to understand uh, the automorphism group. And usually, if the graph has very little symmetry, then it won't have a large automorphism group. The automorphism group will be very small. As you saw in the homework, you just remove one edge from a very nice symmetric graph, and suddenly its automorphism group just drops dramatically in size. Um, there's another very interesting question on the automorphism group of the Quaternion group. So this again, I don't know of a simple like with the Peterson graph. I was able to give you a very simple explanation for why the automorphism group is S5. Uh, Here, I don't know of a simple way to proceed. I mean, you need to kind of just work it out. But one thing that you can keep in mind is that so the group has order 8. So potentially again, uh, uh, you have you have you know 8 factorial possible permutations that you have to sort through. Uh, but uh, but you don't really have uh, you don't really have to do that. There's a lot more structure here which you can exploit. So as you know, the quaternion group consists of elements plus or minus 1, plus or minus I, plus or minus j, plus or minus k, and you have ij is k, jk is I, ki is j, and then you have I squared is j squared is k squared. Yeah. So now, if you look at the elements, you have elements. So you have the identity element. You can say its order is 0. You have minus 1. Its order is 2. And then you have plus or minus I, plus or minus j, plus or minus k. Each has order 4. So now, if you want to compute the automorphism group of the quaternion group, what you know is that if it's an automorphism, then it's going to take, uh, uh, it's going to, of course, it's going to take the identity element to the identity element, but also it's going to preserve the orders of all the elements. So minus 1 must go to minus 1. So f must take 1 to 1. F must take minus 1 to minus 1 because minus 1 is the only element of order 2. So now the question remains is what happens to f of I, f of j, and f of k. So you just need to decide these things. And this gives you how many possibilities. So for f of I, you can either take it to, you can take it to uh, one of these six elements of um, order 4. So f of I could be one of, there are 6 possibilities. And then once you fix f of I, you must ask yourself, what can you do to f of j? And then once you fix f of I and f of j, f of k will be completely determined because ij is equal to k. So f of I, f of k will be f of I times f of j. So you just need to work through uh, how many possibilities there are for f of j having fixed uh, the 6 possibilities for f of I. So one thing, for example, if f of I is I, then f of j cannot be uh, minus I, because uh, right, because I squared, uh, I inverse is minus I, and so you cannot take j to uh, the inverse of minus I, because I and j are not mutually. You cannot take f of j to be the inverse of f of I, because j is not the inverse of I. So maybe I won't spoil the entire fun for you, but this is the main thing that you have to figure out for each of the 6 possibilities for f of I, any of which is possible. What are the possibilities for f of j, and then f of k is completely determined. So that's how you compute the automorphism group. But generally, when you're talking about the automorphism group of a group, there is a general principle, which is the inner automorphisms and outer automorphisms. So what is this? So if G is a group, then G, for every G in G, we get an automorphism phi sub G, G to G, called the inner automorphism corresponding to G, where phi sub G of X is Gx G inverse. So this uh, G goes to phi G is a homomorphism from G to aught G, where by this I mean automorphisms of the group G. This need not be injective. It's easy to see that. So let's call this thing phi, or phi, maybe capital Phi. Phi is not injective. Kernel of phi consists of all those elements G in G, such that Gx G inverse is equal to X for all X in G, right? That's obviously the definition of the kernel. It's the elements G in G such that phi G is the identity map on G. So, but this is the same as the center of G. The set of elements of G which commute with all the elements of G. Because Gx G inverse equals X says that G and X commute. So G commutes with all the elements of G. So that's the center of G. So what you have is, usually this is denoted by ZG. So you have the center of G, and so and this is not surjective either. Not every automorphism is necessarily an inner automorphism. For example, if you have an abelian group, then it doesn't it is equal to its center. So every phi G is the trivial automorphism, and so this is the trivial homomorphism from G to automorphism of G. So there's an example where this is not surjective. So this is not necessarily injective. Kernel of phi equals center of G, and also not necessarily surjective. However, the image is called the inner automorphisms of inner automorphisms of, so image of phi is called, and it's denoted by in G, and this is a subgroup of aught G. And in fact, it turns out to be a normal subgroup of aught G. It's not difficult to prove, and you can form the quotient group aut G mod in G, and this is called the group of outer automorphisms. So it would be very interesting to compute what these things are for our favorite example of a group, namely the Quaternion group. Okay, so Bharat has a very interesting question. He says that I mentioned groups in metric spaces. Well, in a way, actually, a graph itself can be regarded as a metric space. So a graph itself is a metric space. What is the metric? Distance between x and y is the length of the shortest path from x to y. That is the minimum number of edges that you need to traverse to move from x to y in the graph. And that has all the properties of a metric. And then what you can show is that aut gamma consists of all those uh, f from, so suppose we have gamma as ve, v to v, such that, so we can call this d gamma fx fy is equal to d gamma xy. So all the distance preserving bijections from v to v turns out to be the same as the automorphism groups if you define the distance using the graph structure. So for example, if we have this Peterson graph, um, well, here's a picture. So the distance between the vertices 2 and 5 is, so there's a path here, 5, 10, 7, 2. That's of length that has 3 steps in it, right? You have to go through 3 edges. But that's not the shortest path. Actually, the shortest path from 5 to 2 is just through 1. So there are 2 edges. So the distance between 2 and 5 is 2. Uh, in this graph, the maximum distance between any 2 points is actually just 3. You cannot find points which are more than distance 3 apart. Uh, and so you can think of a graph as a metric space. But more generally, you can talk about the automorphism group of a metric space. Um, and so this is how groups enter geometry. So if you know what a metric space is, then what you can talk about is aut of xt is the set of all functions from x to x such that uh, for all x, y in x, the distance between fx and fy is the same as the distance from x to y, and we will assume that this function is invertible, so all bijections. We need, so in the graph case we didn't need to add this because the graph was finite, and even for some infinite metric spaces you don't need to explicitly mention this, but we in general you may need to have this bijection condition. And so here's, let's look at an example. And the most we all live in a metric space. So we live in the metric space, Euclidean 3 space, R cubed. Okay, and that's the space x, y, z coordinates with which you can model the universe. And the distance is the Euclidean distance, so which is given by square root of x1 minus x2 squared plus y1 minus y2 squared. right? The usual Euclidean distance. And you can ask, what is this group? And this is a very important group in physics. It's the group of rigid motions. Every automorphism is of the form rotation and a translation. Rotation means that you have a fixed axis and you rotate by some angle about that axis, and translation means you keep everything parallel and just move it from one point to another, namely you add some constants to the coordinates of your point. So so certainly, automorphism groups also occur in um, such situations. Okay, so are there any other questions? Okay, so I think, yeah, this read thing, let me explain once again, since was sort of introduced in an ad hoc manner in the assignment. So, so maybe, so let me just focus on Reed product with the symmetric group. So, what is the meaning of? So, this is called G Reed SM. So that assignment problem, yeah, it's there's a typo in that in assignment in the problem. Which one is it? It's not quite consistent with what I'm going to say now. Problem 8. Hmm. Yeah, so let me just talk about this. So this is a semi-direct product where, so remember, you have a semi-direct product when you have this group acting uh, on this uh, normal subgroup. So you have this n semi-direct product H. Uh, so here now, my this thing, usually this is written like this with this group on the right. So that makes life a little tricky. You need a right action. So when so this H acts on n. So how do you do it? So the Gn, so Sn acts on Gn by so sigma belongs to Sn, and I wanted to act on. You know what? Let me avoid some confusion here and write it like this: Sn semi-direct product G to the power. So sigma belongs to Sn, acts on n element, an n tuple in G, G1, G2, Gn by just G sigma 1, G sigma 2. G sigma. And with respect to this, you define the semi-direct product with respect to this action. And that is called the Reith product. Um, but there's a more general thing. So suppose you have a group G acting on a set X. So in this case, the group is, maybe I should call this group, yeah, maybe I'll call this group S, just to, because it's going to play the role of the symmetric. So so in our example, we had Sn acting on the set 1 to n. Then you take and you have a subgroup H. H is a group. Then with respect to this action, you can define S Reith. So the Reith product is going to be H to the power X semi-direct product S, where uh, sigma belongs to S acts on. So an element here is of the form. Uh, so if X is X1 Xn, then an element here is of the form Hx1 Hx2 Hxn, and it's just going to be H of Gx1 H of Gx. With this is the action. Oops, what happened? Hey, what happened here? I think I've lost my some glitch. Yeah, and then you just take this. This is a group with component-wise multiplication, and then you take the semi-direct product, and that's a Reith product. But this is the most common example of a Reith product. You usually take Reith products with the symmetric group. Okay, so anyway, you have more questions? Maybe Vishwanath, would you like to add something to?
Yeah, maybe I just wanted to say a few things about the Silo theorems, which is just just the material of the last week, more or less. So just make a few brief remarks. So Amrish, shall I go ahead and share? Yeah.
Yeah.
Okay. Yeah. So um, so I was having some trouble getting this to work. Sorry. sorry, a second. Okay. So let me try this again. So let me just check my video and see if this works. Okay. Okay, is the screen visible?
Yeah, it's visible.
Okay. Yeah. So yeah. So I just wanted to say, make a couple of brief remarks about the Select theorems. So the three parts of the theorem, of course, you've probably seen what they are, and you've probably seen them before as well. Uh, but among the best ways to really understand what are the various possibilities in terms of how many p-silo subgroups there can be and so on. Uh, one of the best ways to actually play with some very concrete groups and see what happens in those cases. So, for example, if you take the symmetric group, G equals Sn for various n's, and sort of play with various primes P, which divide the cardinality of this group. So the cardinality of Sn is, of course, n factorial. And you can sort of look at various primes between 1 and n. So they're the only ones which can divide n factorial, and sort of see what happens in various cases. So some of the simple ones are there in the problem sessions that are the videos, the problem session videos. But here's one other problem which is sort of interesting in its own way. So if you take P equals n itself, for example, so then one is looking at the symmetric group SP and trying to study its p-silo subgroups. Okay, so in this case, the cardinality of the group is p factorial, and so the number of powers of p that divide it. So it's just 1, 2, 3 till p. So there's just exactly one power of p which divides this p factorial. Okay. So in this case, the p-silo subgroup, let's call it H. That's the p-silo subgroup of the symmetric group. So H is the p-silo. So this p-silo subgroup has cardinality p. Okay, in other words, well, what's the group of cardinality p? It's just the cyclic group of cardinality p. Okay, and so the question is, well, we know it exists by the Select theorem. So let's see if we can actually explicitly find the subgroup or subgroups. So what do we need to do? We just need to pick an element of order p. So here's an example of such an H. You just pick any element of order p. So in this case, you can just take the element, let's say, take a p cycle. That's an element of order p. Let's take the cycle 1, 2, 3 till p. Okay, so if you call this the element A, then you can just take various powers of A. Take all the powers of A. So that's a cyclic group generated by A to the P minus 1, and A to the P is, of course, the identity element of this group. So I'll just come P. So here's a P silo subgroup, the cyclic group generated by the P cycle 1, 2, 3 till P. Okay, so of course the question is how many other P silo subgroups are there? So one of the silo theorems tells you something about that. So firstly, well, that's the third silo theorem, which says that the number of P silo subgroups, that number is firstly congruent to 1 modulo P. Okay, so what do we know? So let's just call this NP is the number of P silo subgroups. Okay, of this group. What the third silo theorem tells us is that whatever this number is, it's, well, we know two things about it. Firstly, it's congruent to 1 mod P, and secondly, it divides the cardinality of the group. Okay, that's the other thing we know. So NP is also something which divides the cardinality of the group. In this case, the big group G is just S. Okay, so now, well, let's see what we can say about the number of P silo subgroups. In this case, we can explicitly construct all of them. Okay, how does one construct P silo subgroups? Well, let's for the moment think about it in terms of the second theorem, silo theorem, which says that all P silo subgroups are conjugates of each other. In other words, if you get one P silo subgroup, then you can get all the others by just looking at conjugates of the one single kind. So you can look at all conjugates of G H G inverse, for different G's, take all conjugates of H. Well, what is that? You just have to conjugate every single element. In particular, you conjugate the generator. So it's like taking the generator GA G inverse of that cyclic group. G A square G inverse is just nothing but GA G inverse the whole square, and so on. Okay, in other words, what you construct here, if the original P silo subgroup H was just the cyclic group generated by A, this is the cyclic group generated by the conjugate of A, GH inverse. Okay, and observe that the cyclic group generated by this conjugate is nothing but, sorry, this one again. So the cyclic group generated by the conjugate is nothing but, well, what is the conjugate of a P cycle? Well, it is just a different P cycle, right? So recall, if you conjugate an element with a certain cycle structure or cycle decomposition, you get another element with the same cycle decomposition. Okay. So in other words, this is another P cycle. Okay? I mean, we knew that to start with. We just want to think about it in terms of the second silo theorem. So what is it? Well, what are all the P silo subgroups in some sense? They are of the following form. You just pick an element B whose, you pick an element B whose order is P. So look at the cyclic group generated by P, where B is an element of order P. In other words, it's a P cycle. Okay, so what are the elements of order P? Well, they are of the form, they're just some P cycle. You just put together these P numbers in. So what are the various possibilities for B? B is just some P cycle. So you can look at some P numbers arranged in sequence, right? So that's, sorry, this thing is misbehaving here. So what I mean here is that B is a P cycle. Okay, and okay, so what does this imply? It says that, well, how many such B's are there? I can calculate this number of B's, and this number is just, well, we have the standard formula for computing the number of P cycles. Sorry. So this number is just P factorial divided by, so just look at see if it works. P factorial. Sorry, let me. Okay, so let's just compute it quickly. It's P factorial divided by so it's P factorial by P in some sense. So we are looking at okay, so still not able to get this to work. Okay, so maybe we'll just let me just say this orally and maybe leave it for you guys to try it out. So the thing I was trying to get at is try to compute the number of elements of order P in the group SP, and P minus one of them together are part of each subgroup in addition to the identity element. Okay, so using that, one can figure out how many P silo subgroups the symmetric group SP has. Okay. And that number turns out to be P minus 2 factorial. So one just uses the formula for the number of P cycles and use the fact that you put P minus one of them together along with the identity to form a subgroup. Okay. And there are P minus 2 factorial of them. And the third silo theorem, interestingly, says that P minus 2 factorial, therefore, must be congruent to 1 mod P. Okay. So this is an interesting theorem of elementary number theory called Wilson's theorem, which sort of says that in a slightly different form, it says P minus 1 factorial is congruent to minus 1 mod P. Okay, so that's sort of what I wanted to say. In general, it's nice to play. I mean, the symmetric groups are maybe the richest source of examples for pretty much any of the theorems that we're likely to see. And the silo theorems are especially nice to try to play with, trying to find silo 2 subgroups or silo 3 subgroups for the various symmetric groups. Yeah, so sorry about the technical glitch, couldn't quite get this thing to work.
Yeah, so I think I skipped one question which Krishna had asked. Should I do that?
Yeah, go ahead.
Yeah, sorry, it was kind of, I somehow missed it. So it's a very interesting problem, in fact, in the first assignment. And in that problem, there's a certain permutation which is given. It doesn't matter much for this explanation which permutation is given and so on, but a certain permutation is given. I guess it was the permutation one. Can you see this? Yeah. Yeah, okay, so I think it's visible. So the permutation was so many windows open. I'm having trouble finding the correct one. Ah, yeah. 2143 214537. 214537. So let's just so question is how many subsets of the set of integers 1 to 7 are fixed by W. And so let's just get a visualization of this permutation. There are 7 points. And what we see is that this permutation, it takes 1 to 2 and 2 to 1. It cycles 3, 4, and 5. And it takes 6 to itself and it takes 7 to itself. Now, let us just ask ourselves in view of this, when is a subset fixed by this permutation? And so, for example, you can see that the subset 1 comma 2 is fixed by this permutation because 1 goes to 2 and 2 goes to 1. But a proper subset of this is not fixed because if you just take only 1, for example, then 1 will go to 2. So this singleton 1 is not fixed. Similarly, 3, 4, 5, this is fixed, but you can't take any proper subset of this. So what you can try to, the fact is that the subsets that are fixed by W are union of its cycles. So each cycle is either fully contained in your subset or disjoint from your subset. And so since there are 4 cycles here, there are you have a choice each time you're given a cycle, you can decide whether to include it in your subset or not. And so for example, if I choose that I will include uh, this cycle and say this cycle, then my subset that is fixed by W is going to be just S is equal to 1 to 6. And you can see that this is fixed by W because 1 goes to 2, 2 goes to 1, 6 goes to 6. So this is fixed. So in each case, I have a choice. For the first cycle, I can decide, do I want to include it in my subset or not? Then for the second cycle, again, I have a choice. Do I want to include it in my subset or not? And so I have 4 times I have to choose between yes and no. And totally there are 16 choices. So that means there are, the answer here is 16. That's the solution to this. And so you can now easily apply this to any permutation. It's just 2 to the power number of cycles in the permutation. So that was somehow the idea behind this question was that we should discover this fact. But anyway, if you didn't spot it, here it is now. So I think that was the question I missed. Krishna, if I missed something else, you could just type it into the chat. Last problem on this side. It was yeah. So this is okay. So the last problem on assignment 2 is so the group in question is automorphisms of bijections R to R which preserve the distance between points and take integers to integers. So yeah, so here and now we have R is R of x is minus x and uh, P is P of x is x plus 1. So this is translation and this is reflection. Okay, so firstly, let me just explain. So this group is a very well-known group. It's called the infinite dihedral group. So let me just recall for you firstly what is Dn. So Dn is defined as uh, Dn is defined as Z mod nz semi-direct product C2, where C2 is the cyclic group of order 2. The non-trivial element here takes uh, epsilon takes x to minus x, right? So that's the dihedral group, and D infinity is just defined to be Z semi-direct product C2 with the same principle. Epsilon x is minus x, and this here is the R, and this is the group generated by. So so that's the realization as D infinity, and that's the realization as Z semi-direct product Z mod 2 also. So so that's more or less, yeah, that's the explanation. So this is I talked earlier about rigid motions of three-dimensional space. So if you don't have this condition sigma z equals z, then this is actually R semi-direct product T2. And these are the rigid motions of the real line. Both these groups, this actually relates to another question that's been asked on the forum, which was asked uh, by Vijay. So Vijay was asking about Lie groups. So these two are examples of what are called Lie groups. Uh, Namely the rigid motions of R cubed and the rigid motions of R, which is R semi-direct product C2. These are both examples of Lie groups. They are groups where uh, the group elements are not very much in contrast to finite groups. These are groups where the group elements depend on continuous parameters. So when you define the group of rigid motions of R cubed, you have these rotations, and the parameters defining a rotation are an axis, which is given by a unit vector, and an angle, which is given by a real number between 0 and 2 pi, or rather, an element of R mod real numbers modulo 2 pi times the integers. So these are groups where the parameters defining the points are actually continuous. And in more sort of modern language, you would say that these are groups which are also uh, topological spaces. So the Lie group is a group which is also a topological space, and the group operation is supposed to be continuous. Well, that's actually what is called a topological group, but we need something even stronger, that this topological space looks in if you look at any open neighborhood of a, we're not going to look at Lie groups here, because understanding them involves an understanding of manifolds, which I think I can't assume in this course that people have. So yeah, and just to clarify on this, Z semi-direct product C2 is the same as D infinity. So both answers are correct for problem 15. Okay, so yeah, are there any more questions? Okay, yeah, I'm happy to hear that. Krishna, you asked very nice questions also during this session, and I hope you'll keep the questions coming. It's nice to know that students are engaged in this course. So, and Vijay, yeah, you could email one of us if you want some advice on of that sort. But I'm not sure. Yeah, we'll see what we can do. Sorry, I meant Bharat. Yeah, so you can just email one.
So the end of the session.
Yeah, I think we can end, right? It seems
Yeah.
like there are no more questions. So
Okay.
thanks a
Thank you.
lot.
Thank you for coming. Yeah.
So
Have